if I swing this, this will stay in equilibrium. If I go faster, it'll go up. If I slow down enough, it should drop. There we go, it's slowly dropping. So there is an optimum speed, especially if it were frictionless. All right, so I've got my force diagram here, done. What is the direction of acceleration of mass 2?
Should there be none if it's in equilibrium?
Absolutely. So we can choose our positive direction any way we want. It has absolutely no bearing if we choose it up or down. It doesn't have to match this, the mass that's swinging in a circle. So acceleration for, what's the direction of acceleration for this mass? Someone take a shot at it.
It looks like counterclockwise. Don't you have an arrow?
The way I've drawn, I don't actually have an arrow there. Oh, I do have an arrow there.
Yeah.
So that would be counterclockwise. However, that's not the direction of acceleration. That's the direction of movement. Is it traveling in a circle?
Yes.
What's the direction of acceleration for something traveling in a circle at a constant speed?
There's no acceleration.
Oh, no, there is.
Constant speed. You said constant speed, right?
I did say constant speed.
Going out of the circle?
Or
Toward
toward what?
the center of the circle.
Towards the center of the circle. That's the whole bit that we just went through. With something traveling in a circle at a constant speed, the direction of acceleration is towards the center of the circle. So that's centripetal acceleration. So the acceleration in this for this one is towards the center, the way we have it drawn right there. So we've established our directions of acceleration. What's next?
Coordinate axis.
All right. So how do you want to set them up for mass 2? There's no acceleration, so it is vertical forces. Is that a gesture for which way you want to make positive? I'll take it just to move this on. On my J, what's up to be positive? For this one again, it really no impact. Doesn't matter up or down. Just pick one and live with it. All right, this one. What is our coordinate system here? With acceleration, the way it's drawn right there, going to the left. So how do we set that up?
Positive to the left and up just for consistency.
All right. So we'll make that the I hat direction, and make that the J hat direction. Do I need to decompose anything?
No.
All right, that's done. Equations of motion. How many equations of motion will there be? Did you think of that? All right. So we got the 2 for this one and the 1 for that one, similar to the one that we just did with the book and coffee mug, so we just, I'll break anything up here. All right, so we'll have an I hat equation, we'll have a J hat equation, and we'll have our, because I labeled it as a plus sign, our plus equation. Okay. Somebody take a shot at one of the equations. Like you mean it.
0.
0. 0. All right, one equation down. That's why you go first, is that you get the easy one. Next.
For J hat, is it gonna be Y1 minus W1 equals NA?
I didn't label it as Y1, but it looks like you did, so we'll throw that in there. Is equal to what?
M1A.
Small little issue.
Said what was positive, right? We said what was positive and what was negative.
Right, so up was positive here, so I have no problem with that. Or are you going for something else? All right, let's do the other equation, then we'll come back to it. There is a small little problem. It's not gonna require a complete rewrite. There's just one small little adjustment we need to make. What's the last equation? So wait, we still make the left side of the last equation. Yeah. There's only one horizontal force here, it's Ft. It goes right there. That's the entire force. All right, now the right side. Nope. Unless you were answering a previous question I asked. Did somebody say it? What's the template? What's the main thing that we're plugging into? What's our pattern for setting up these equations? I have only one horizontal force. That's got to be equal to the mass times the horizontal acceleration. All right. Now, sort of hinted at already, but what is the problem with the second equation?
0.
Yeah, should be 0. Yeah, that'll really mess up the math if you miss that part. And again, the whole reason we set up our system like this is so that one of the two equations for that mass is equal to 0. All right, now substitution. We have a formula for weight. So we're gonna do that plug-in. But we now have a formula for acceleration. Because again, circular motion, there is a formula for it. So this now becomes tension is equal to mass 1 times v squared over r. y1 minus m1g equals 0, and the last one is we have tension minus m2g equals, or ft minus m2g equals 0. And so now it's time to solve. We're trying to find V right here. This middle equation right here, the y1 minus m1g equals 0, that doesn't really help us at all. There's no friction involved, so that doesn't do anything. So how do I simplify this? Not yet. Gotta do something else before we do the square root. Remove the f? Move the m. Oh, okay. Before we start isolating v, I do recommend one other thing. You could do it this way. I think it's a little bit, something that will simplify life a little bit better. We do one other thing first before we get to where you're going. Because the trouble is, if I just start isolating v like here, I still have this tension that I need to get rid of. So how do I get rid of tension? Division is not going to do it for us here, because then it'll just show up on the other side.
We know tension minus m2g equals 0, so force tension should equal m2g. Substitute.
Or what I've done in the past, just added two equations, so that, well, except tension we'd have to subtract an equation. But tension is equal to m2g, the weight of what's hanging. So we plug that into here. We have m2g equals m1v squared over r. Now we're to the point where Amaje was. How do we solve for v? Or what's the first step to solve for v? All right, so let's start isolating v, so we multiply both sides by r. So I have m2gr is equal to m1v squared.
Divide both sides by m1.
So v squared is equal to m2gr over m1.
Take the square root of it.
Then we get to the square root. And so we end up with the speed that it has to go in order to maintain that constant distance. M is the square root of m2gr over m1. And so let's make this 2 kilograms and make this one 5 kilograms. So that's equal to the square root of, so that was 2 times 9.8 times 0.5, at least I did give you that beforehand, and divided by 5. Units?
Meters per second.
Yep. So as long as the thing's going about 1.4 meters per second on a frictionless surface, it will maintain that distance from the hole. All right, questions to hear before I make it slightly more complicated. We're now dealing with the situation that I demonstrated. I have some angle theta, that it's gonna sag. This is the big difference between the demonstration I did with the tube and the problem that we just did is that this is not horizontal. The string's not horizontal. As before, mass 2 is in equilibrium. I know it's going to shock you, but we're going to start with the force diagram. So I got my mass 2 here. We'll throw the string into it. And then mass 1 there. All right, lay it on me. What do we got?
Don't have another.
All right. And let's assume an ideal rope or string. Yep. So I got tension acting here, tension acting here at that angle theta, and tension acting down and tension acting up. All right, one string, we got both ends taken care of. All right.
There's no friction.
All right. Where's the normal force pair?
Is it on the rope and what I'm assuming is a pipe?
Yeah. Yeah. So there's a normal force acting somewhere in this general direction at that point in time, and there's another one acting back on the pipe, but I just didn't drill the pipe, so I'm not gonna worry about that part. Normal force done, and gravitational force. Is there any?
There better be.
Yeah, I hope so.
Should be pulling them both down, both off to it.
All right, so I've got W2 down here, and W1 right there. All right, direction of acceleration. Mass 2, what's the direction of acceleration? Let's pick the easy one first.
Stop.
It's accelerating upwards?
Sure. There is none.
That's right, there's no acceleration, that was the equilibrium bit. So no acceleration. I assume you were answering the next part of the direction of positive, but, so, while we're here, we'll make that up. I'm just gonna call that J2 hat instead of plus, why not? Over here, what is the direction of acceleration? And this is the place where probably the classic mistake is about to come up. Or not, maybe it's you'll get it right without having to have that awkward pause. What is the direction of acceleration of mass 1?
It's still spinning like in the last time, correct?
Yes.
And it's gonna be, towards the center.
Which is which direction?
In this case, it would be left.
Not at an angle? Or straight left?
I'm gonna say straight left.
It is indeed straight left, because it points towards the center of the circle. This thing is traveling along, presumably in a horizontal path right here. That's the center of the circle. Center of the circle is this way. It's not part of the force diagram, it's a separate element. That is the direction of acceleration. The classic mistake is to put it up in the direction of the rope. It is not. Oh, done that. All right, so we got the acceleration. Now the coordinate system. We've already defined the coordinate system for this. For this one, what coordinate system should we use?
Positive to the left, with acceleration,
Okay.
and then up is positive.
Decomposition. Do we have to decompose anything? All right, I got a nod on yes on that. What do we have to break up?
Tension.
Yes. It's the only thing that's not parallel or anti-parallel to the axis. So tension is going to get broken up here. I know that tension's acting at an angle theta here. And we'll try to draw it at least closer to the way I've drawn it over there. And so we have a horizontal and vertical component. What is the horizontal component?
FD cosine theta.
And that would make the other one FD sine theta. So my mass 1 here, we now can break it up into, I have weight 1 acting down, I have FT sine theta acting up, and FT cosine theta acting towards the middle. Equations of motion. I'll have 3, so I've got my I hat, I1 hat, J1 hat, J2 hat.
For J2 hat, it's gonna be, the tension force minus weight to equal 0.
Okay, one down. Run with it.
J1 hat is gonna be FT sine theta minus weight 1 equals, it's gonna be 0 again?
It will be 0.
And then I is gonna be FT cosine equals, and then
And that'd be M1. Okay. Questions to hear about how we got this far? All right, substitution. We know we have one for weight. We have one for acceleration. So Ft cosine theta is equal to M1 V squared over R. And then Ft sine theta equals M1G, and Ft is equal to M2G. Now there is a little trick that we can do here just to make life a little bit simpler. So we did acceleration as v squared over r. There's another form of it that actually is a lot more convenient in this situation. So let's go back to our circle here. If I have something moving through an arc, some distance s, we have this relationship between the arc length, the radius, and theta there as something moves in a circle. So S is equal to R theta. So the change in distance would be equal to R times the change in theta. And then it takes a certain amount of time, so just divide by time. So this right here is basically a distance divided by time, which is
velocity.
Distance.
Oh, displacement?
No,
No.
we're not dealing with a vector here.
Okay.
So what is distance over time?
Speed.
Yeah, speed. Is equal to R times the change in the angle over time, or the angle over time is angular speed. This is an omega, is the letter, and it stands for angular speed. So if an object goes around a circle in 5 seconds, so the period is 5 seconds, capital T for period, which is the time it takes for a revolution to happen, or one cycle to happen. Then if it goes in a circle, that's 2 pi radians divided by 5. So that's radians over 5 seconds. And that's going to be 1 point, somewhere around 1.3, whatever the number actually is, radians per second. That is the angular speed. So if I look at our formula there for acceleration, if I know that A is equal to V squared over R, and V is equal to R omega, so this just becomes R omega squared over R. So that becomes R squared omega squared over R, which is R omega squared. So we have an alternate form for centripetal acceleration that's equal to M1 omega squared R instead of V squared over R. This actually is of great convenience. So if I'm solving for V, or what am I solving for? We'll just sort of explore for right now. So I have this tension times the cosine of the angle which it's sagging is equal to M1 omega squared R. Now this doesn't necessarily look, I can imagine, that we've simplified it, but there is one more thing we can do. R is the radius of the circle. R is the distance from here to here, that's R. Theta is that angle right there. If I know this distance, L, what is the relationship between R and L? Let me draw just that triangle there. That length there's R, that's L, this angle is theta. What is the relationship between, that's a right angle there. What's the relationship between R, L, and theta?